So that limits where I could stick that formation in, because I've got to account for both of those shells. Now here I've got a ginkgo leaf. Boy, that narrows it down even more. This is the only place where all three of them would occur together. If I had any of these skeletons, like a T-Rex skeleton, well, that would eliminate any of this. I wouldn't expect to find these two together. And here's another little brachipod over here. Here's a starfish kind of thing. And you can see that this would work if I had a brachipod, a pelecypod, a brachipod, a starfish. They'd all fit. And this is where they'd fit into, is this B category here. All of these guys, I can play the same game, and here's where all of these things overlap. There. So I'm not looking at just a single fossil, but I'm looking at the entire group of fossils, what we call the fossil assemblage, the assembly, okay? The more I have in the assemblage, the more detailed I can get in determining the time range. And the more samples I can collect from a wider area with that assemblage, the more assurance I have that I'm on the right track. So this helps me now, besides the lithology, because lithology can change. We've got facies changing in a lateral sense, but still the same time package. So here's a way that fossils can tell me, same time package, despite the change in lithology. Here you can kind of see an example of that. I've got a number of outcrops here, and first of all, I'd go, oh, shale, 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 shale. That looks like a unit, it's the same. And sure enough, they all contain little brachiopods, so I just hooked those right up as that was the original package. And okay, here's a sandstone package with a brachipod in this one, and a brachipod there. There's my next package. So far I'm on track, right? Pretty horizontal. Got the older trilobites. Brachiopods are a little younger, so that looks good. And then I've got this one, a limestone package with an ammonite. Uh-oh, don't have it here. I've got it over here. And then I've got a sandstone package with a brachipod, a sandstone package with a brachipod, and the same thing over here. Well, the only way I can hook this up sensibly is this top unit looks like it matches all three locations, but this limestone unit is missing here. And even though the section's conformable here and here, I've got an unconformity in this part of the section. It's been eroded out there. The fossils saved my analysis here, didn't they? And you'll notice that not everything's flat and straight. Erosional surfaces are going to be kind of wavy and up and down. River channels are going to cut through. It's going to, erode in some areas, while at other times, right next door on the floodplain, deposition is going on. So fossils are a really good way to correlate the strata all over the place and kind of hook things together. The first guy to figure this out was a guy by the name of William Smith. He was actually a surveyor and an engineer building canals over in England in the early 1800s. And he started to notice that the rocks contained fossils, and as he tried to, the canals were cutting through the strata, and he was trying to figure out how to predict what would come next and what the structures were. And he noticed that the fossils were kind of lining up with what he was seeing as far as structures, and how to correlate one set of rocks to another set of rocks at the other end of the canal. So he started to map all of Britain, and he did. He produced the first geological map of Britain, which still exists, still hangs in the hall of the Royal Society. William Smith was an interesting guy. He was kind of what you would call probably the merchant class of England at that time. He was not a royal. And to become part of the Royal Society, that word kind of jumps out at you, doesn't it? And even though he did an incredibly insightful and brilliant piece of work, he was not voted into membership because he wasn't one of the royals. In fact, William Smith had spent time in debtor's prison at one point in his life. It wasn't until he was in his late 70s, early 80s, that finally the likes of Sir Isaac Newton and Sir James Hutton and some of the other people that were in the Royal Society finally said, this is stupid. Why isn't he in the Royal Society? Look at what he's done. And he was eventually, toward the end of his life, voted into membership. So it was kind of neat. But he carried a chip on his shoulder for a long time because he knew he'd done a brilliant piece of work, and the caste system that existed in England at that time prevented any recognition. But the world now fully understands what he gave us. This is the map that changed the world by Simon Winchester. Winchester got his BS degree in geology from Oxford University and went on to become basically a journalist and a reporter. And he's written 4 or 5 really good books. This is one of them. Krakatoa, about that volcano, is another one. Very readable, very enjoyable. And if you want just a good read, a good story, check out Simon Winchester and check out this book. I think you'll find it's a fascinating story. Okay, here's another thing we can use. Remember we talked about having a closed system so we had a baseline for comparison? Well, here's kind of the same principle in a little different way. If I have a unique bed of lithology that shows up in every one of my outcrops, and that bed is so unique that I know that's got to be the one that hooks together, that sets the stage for how everything else hooks together, doesn't it? We call it a key or a marker bed. They're the key to the section. And there's some criteria to make a good key or a good marker bed. One of them is it needs to be produced by a fairly rapid geological event. If it's going to represent time, it needs to be something that's a short blast. If it's spread out over a long period of time, that's not a very accurate gauge, is it? So we want it pretty short. Something like a volcano that puts out lots of ash, that's a great marker bed because all that ash, it probably only erupts for, a few weeks, a few months maybe. Geologically, that's poof, and it's gone. So an ash bed says, oh man, I know just when that happened, when that volcano was erupting. So that's pretty cool. The other thing is you want it to be a widespread event. It doesn't do you much good if it only covers a couple of outcrops. You want this thing so you can just trace this marker bed all over the place. You can hook together rocks in Washington, rocks in Oregon, rocks in Montana, and you know that key marker bed, so whenever you see it, you go, I know where the section starts. And volcanoes are great for this because the ash spreads all over the place. Here is one that was Mount Mazama. Today, it's a crater lake. It was a huge volcanic cone. It exploded, spreading ash all over the area. You can see the area here, the whole Pacific Northwest. As it did that, the cone collapsed. And as it collapsed down into the magma chamber, it left a big hole in the ground that filled up with water and became Crater Lake. So what you're looking at here are really the outer flanks of that big volcanic cone. And you'll notice Wizard Island here in the middle of the lake looks a little bit like a volcano, doesn't it? And that's because it is. It is the growth of the next stage of volcanism. It's actively growing. The magma chambers down underneath, and Wizard Island, although not much is going on now, it is considered active. So a new volcano is growing to replace the old one. But here's this ash that came down all over the place, and you can see it here. The bottom part's white, the top part's kind of gray. And we're going to talk about that when we talk about volcanoes and magmas, and you'll see this slide again. But right now, what I want you to kind of think about is the fact that this widespread, very distinctive ash now is a key marker bed for this whole part of the country. Whenever I see it, I know right where I am. Let me show you another example that's even more striking. This is a road cut down in Layville, Tennessee. And when you look here, you can see there's a kind of a layer right through here. This is known as the Milberg bentonite. And bentonite is a clay. And that is what volcanic ash breaks down and weathers into, is that type of clay, a bentonite. And here's another bentonite here. This is known as the dikey bentonite. So those are key marker beds. They're all over the place. They're quick events, and you know that these were put down by volcanoes, ash flows. But what's really cool is I can look for these two markers and carry them all over the place. Here I am, this is the eastern part of the United States, and notice how I can carry these two layers all the way through Michigan, into Wisconsin, Minnesota, all the way from Tennessee. Basically, the whole eastern half of the United States is keyed with these two marker beds. Here's an even cooler part. When we go over to Scandinavia, to England, all the way into Russia and Germany, we see the same two marker beds. Whoa. That's a big area. And we didn't understand how this could happen over such a huge area, the whole eastern half of the United States, basically the whole western half of Europe, and the Atlantic. Wow, what was going on? What kind of a volcano produced that widespread an event? But then as we developed plate tectonic theory, it fell into place. These were explosive volcanic events that occurred when what we called at that time the Iapetus Ocean, it was a precursor to the Atlantic. Europe and the United States were right next to each other. It was all one continent. And as it started to rift apart and break apart and drift away from each other, the Atlantic, called the Iapetus, started to open up. So at the very early stages of forming the Atlantic Ocean, there was a ring of explosive volcanoes, and what we're seeing is Western Europe and Eastern United States weren't that far apart. They were all part of the same landmass. Now it made a little more sense. But the cool thing is we've got these two key marker beds, and man, you see those in the rocks and you know just where you are. Here they occur down around the Trenton Black River section, some limestones that are, for the most part, they range from about 4,000 to 6,000 feet below the surface here in most of Michigan. And those two units are some of the prolific oil and gas fields in the state. So we really like keying into those. Those really help us out. Okay. So if I want to look at geologic time from the Precambrian all the way up to the present day, represented by the rock units deposited during time, there is nowhere on planet Earth that I can do There is no such thing as a full, complete geologic section. But we can get close. And one of the very few places on Earth is here in the United States. It's the Grand Canyon National Park area here in northern Arizona. It's Zion and Bryce Canyons here in southern Utah. And between those three national parks, we see every geological formation from the Precambrian more than 560 million years ago. In fact, the Vishnu schist, remember we said was 1.8 billion, so we're getting down into the Precambrian. And we can see everything, and we can hook it together by looking at the sections in the Grand Canyon, in Zion, and Bryce. Man, that's pretty cool. They couldn't do that in Europe. For the centuries that they were practicing geology in Europe, it didn't become clear until they saw this. So if I look at the Grand Canyon, you know, there's Powell floating down the Grand Canyon, our Vishnu schist at the bottom, and we go up through a number of sandstones and shales up to basically Toroweap and Moenkopi here at the top of the section. Then it's the plain and it's eroded off. But if I go over to Zion, that's kind of the base of the section over there. And I can correlate the Kaibab limestone with the Kaibab limestone here. It's a good match. And that gets me up through the section, through Wingate Sandstone into Navajo Sandstone and Carmel Formation. Navajo's a gorgeous sandstone. It's old sand dunes. And you'll see the big sweep of dunes as the structure in the sand. And then it's eroded. But that gives me a way of hooking into Bryce Canyon, where Navajo and Carmel are the base of the section exposed at Bryce Canyon. And that takes me up through Wasatch Formation, which is present day. Now, is that not cool? 3 national parks. I mean, besides the breathtaking scenery, one of the reasons that they got made national parks was because of this geology and the fact that this represented what had happened on Earth. It's well worth your time to go. Now, if we look at Michigan in the Midwest, the Midwest was basically represented during a lot of the early Paleozoic as a series of basins separated by ridges. So we have this big basin out here that kind of goes through eastern Ohio, Pennsylvania, down through West Virginia. We have another basin over here through Indiana, Kentucky, Illinois. Another basin over here, Iowa, Kansas. We've got a basin here in Michigan, Lower Peninsula of Michigan. And all of these were high areas surrounding these basins. So the highs were eroding. They were weathering. That material was being carried down into the basins on each side of the ridge, filling in these basins with rock, or sediment that became rock. Now, it would be nice to know that the section here, how to fit it to the section here, to the section there. Things were kind of happening about the same, but you had different directions of deposition coming in off the ridges, and timings were probably changing a little bit. So it's not a perfect match from basin to basin, because different events were happening. But we've got some coals that show up in the section that act as key marker beds. And a few of these sandstone conglomerate packages give us very strong correlations. So we can look at wells that are drilled in these different basins, and we can get a sense of what was happening. And you can see here the Appalachian Basin was the deepest and had the most depositional development. And the Ohio, Indiana, and Kansas ones were all a little bit shallower. And Michigan kind of looks about like right in here. So now, let's say I'm an oil company and I'm drilling wells in these various basins. Well, this gives me the opportunity to take my experience in the Michigan Basin and apply it to the Kansas Basin or to the Appalachian Basin.